So to start off with, we are going to look at non-permissible values for each of these. So in A, well, if we're going to have non-permissible values, what we're looking for is things that is not possible, things that are not possible. So we can't divide by 0. We can't take the square root of a negative. Those are two main things that we learn that are not possible. In each of these questions, there's no square roots. So basically, the only thing you're looking for with non-permissible values is you can't divide by 0. Well, are we dividing anywhere? And when we're looking for dividing, we also have to think that some of these are reciprocal identities. So for example, in A, cotangent is cos theta over sine theta. Notice that you're dividing there. You're dividing by sine. And on the bottom you have cosecant, which is 1 over sine theta. On the other side, you just have cos theta. So what I've done here is I've just changed each of my reciprocal identities. And it's going to be easier with cotangent to change it to cos over sine than it would be to change to 1 over tan. Yes? Well, we're not proving it yet. That's a good question. How come I don't have a line there? Because for the first part, we're just trying to say the non-permissible values. You could put a line there. Because I'm not trying to prove it yet. I just want to say what the non-permissible values are. So my non-permissible values. Sine theta cannot equal 0. That's one of the things that we're going to have out of here. We know that sine theta cannot equal 0. What does that mean? When is theta equal to 0? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. How do we write all of those? All the multiples of pi. Are there any other places that it's equal to 0? No. So only sine theta. So those would be our non-permissible values for A. For B, if we look at things, if we look at rewriting, first of all of our, if I'm looking at this, cos theta equals 1 plus cos theta, and I have a reciprocal one here, which would be 1 over cos theta. What are things that can't equal 0 for this one? Where are we dividing? Cos theta can't equal 0, so one of our non-permissible values. Cos theta can't equal 0. Okay, so let's do that one first. If we do that one, that means theta can't equal, when is cos theta equal to 0? Pi over 2, 3 pi over 2, 5 pi over 2. So depending on how you like to write, you can either do the 2k plus 1 times pi over 2, or since one of them is pi over 2, and there's a distance of pi between each of your zeros for cos, you could write it this way, or you could say theta can't equal 2k plus 1 times pi over 2, because that's writing an odd number times pi over 2. So that's one set of non-permissible values. What also can't equal 0? Right. Notice that you're dividing by this whole thing. Right? Can you see that that's on the bottom of a fraction? If what's inside that green circle is equal to 0, that's going to be bad. So how would you solve that? We know that 1 plus 1 over cos theta can't equal 0. When you have an equation like this, so let's say I do try to solve this equal to 0. So if I'm trying to solve this as equal to 0, so if I'm trying to solve something like this that's equal to 0, and I have a fraction, well, maybe you can see it, right? So yeah, this is one where if cos is -1, you see that it's equal to 0. Now, algebraically, if we were wanting to solve this, if we have a fraction like this, how do we get rid of a fraction? Multiply both sides by cos. So if I multiply everything by cos, if I multiply this whole side by cos of theta, and I multiply this whole side by cos of theta, what happens? Over here, this becomes, because this would get distributed, right? Cos of theta plus 1, and this side's still 0. So algebraically, we can get exactly what you could just see as well. So maybe you could just see that cos theta is equal to -1, but here's the algebraic steps to get that as well. When does that happen? Pi. When's the next one? 3 pi, 5 pi, 7 pi. So theta can't equal pi plus all the coterminal angles with pi. So you could write it this way, or if you're noticing that it's all the odd numbers of pi, you could also write it this way. Make an odd number times pi. So two different ways of looking at that. So those are our non-permissible values. That was just part I. Now part 2, that's what I want you to try on your own on the scrap piece of paper. Come up with proofs for both of them. Yeah. So here are some of your examples of proofs. And we're going to talk about all sorts of things here and little minor details that can make your proofs nicer. So here's the first proof. What this person did is they changed cotangent to cos over sine and cosecant to 1 over sine. And then since they have a fraction divided by a fraction, they multiply by the reciprocals. The sines cancel out and they get cos, and their left side is equal to the right side. A couple of things that I would do in this one, just you're going to find that when you do the sideways dividing, you're going to find that maybe later on when things get busier, it's going to be nice to have a big dividing so you can really remember what is your fraction on the top and what's your fraction on the bottom. Especially if you have more than one thing on the bottom, sometimes you lose part of your fraction when you're writing that way, but in this case it's fine. Another thing that you're going to want to start to do when you work on these is I would leave a little bit more space in between things, just so that you clearly see where one step goes to the next one. Other than that, this proof is perfect. Here's another one. I wanted to show this one because it's a little bit different. So in the first one, cotangent was changed to cos over sine, and in this one, we changed it to 1 over tan. Now when you change things, so notice this is the difference between this proof and the last one. We're changing cotangent to 1 over tan instead of cos over sine. Now as you do a lot of these, you are going to find that often changing to sine and cos will help you out more. But sometimes it's going to be more beneficial to change it to tan. One of the things that can help you realize which one's better to use is look at the other side. Can you see that the other side just has cos? So if the other side had tan, I'd be more tempted to change things to 1 over tan. But since there's no tan on the other side, as far as making that decision, I might choose to change to cos over sine. But you can see that even if you change it to tan, things are still going to work out because we still have a fraction over a fraction, and then you can multiply by the reciprocal, so 1 over tan times sine theta over 1. That becomes sine theta over tan theta, and now you realize, oh, I do have to change tan to sine over cos. So later on in the proof, you realized you needed to do that. And so now you have sine divided by cos. Now, a couple things here. I might make this line longer so you remember which is the top of your fraction and which is the bottom of your fraction. Because sometimes what students will accidentally do here is think it's sine divided by sine, all divided by cos, and forget which is your main dividing line. And then you end up with the wrong answer there. But here, the other thing that's good about this one that I want to point out, when you have a single thing on the top, we have sine theta on the top, and we have a fraction on the bottom. Well, anytime you have a single thing on the top, it is a fraction, right? Because you can write that top as sine theta over 1, just like this person did. And then multiply by the reciprocal, which is cos over sine. Sines cancel out, and you just get cos. Left side is equal to right side. This person would lose a half a mark for getting theta once right there. So it's a good example to You're going to be doing so much work that you want to be careless. Don't be careless. Write things clearly. Make sure you have a theta all the time. Okay? And that is the end of examples of example 1. Now here we have example 2, or part B. This proof. First of all, first thing to do is to change secant to 1 over cos. Excellent. Again, spacing-wise, I'd probably space things out a little bit more so that you can clearly see where one step goes to the next. And then what is happening here is you have to realize, and this is where some of you got stuck, is you tried to multiply by the reciprocal too soon. You can only multiply by the reciprocal if you've got a fraction on the bottom. So on the bottom right now of our fraction, right here, we have 1 plus 1 over cos. That's not a single fraction. In order to get it to single fraction, you can see here they're getting a common denominator. And once they have that common denominator, they add that together and get a single fraction on the bottom. And once you have that single fraction on the bottom, then you can multiply by the reciprocal. The 1 plus cos theta gets grouped together there, and it gets grouped together here. And yes, they are the same, so they can cancel out, and you get cos theta. So therefore, the left side is equal to the right side. This is the most typical way to do these questions, and you're going to get lots of them where you want to get a single fraction on the top, a single fraction on the bottom, so you can multiply by your reciprocal. Again, this is a good example because on the top you have 1 plus cos theta. So it's hard to think that that is a single fraction because they both have denominators of 1, so you can write it as 1 plus cos theta all over 1. We'll look at a couple more examples. So here, this is, again, starts off the same way. We've got a common denominator on the bottom. In this case, we're feeling like, ooh, how do I get the top together? How do I get a common denominator? So you notice in the top here, the person is trying to get a common denominator and doing a little bit extra work. More work than you need to. And then realizing, oh, I didn't need to do this, and reverts back here to the same thing that we had started with. So sometimes that happens. You choose to do something you don't need to, and you have to undo it. And that's okay. Got a single fraction on the bottom, multiply by the reciprocal. So this proof is the same idea as the last proof. Just the one thing in here that's different, because for a while there they thought, oh, maybe I need to get a common denominator of cos for everything, but then realized they didn't have to. And this is fine. The important thing is each step is equal to the step before. So when I'm marking these and I'm looking, does each step match what was before? So even though they changed the 1 to cos over cos, that's not wrong. It doesn't help them in the proof, but it's not wrong. And then they undid that later and kept going. Here's another one of part B. This one is identical to the first one that we saw. And here we have a part B that's done a little bit different. So I'm going to show you this strategy as well. For the most part, you'll probably, the first ones that we saw where we got a single fraction on the top, a single fraction on the bottom, that's what you're going to use most typically, and it's going to work really well for you. But another technique can be seen in this one. We have the secant changed to 1 over cos. And what the person did here, if you're wondering, how did they get from here to here? Because they didn't show any work. They just all of a sudden wrote that next line. Well, you're always allowed to multiply by 1. So to get rid of the fraction on the bottom, the 1 over cos, you can get rid of that if you multiplied by cos. So what this person did is they said, if I multiply the entire bottom by cos, that would get rid of that fraction on the bottom. If I multiply the entire bottom by cos, I have to multiply the entire top by cos. Put that in brackets so that you can see what's happening. Because if I'm multiplying by cos over cos, I'm multiplying by 1, and I'm not changing what it's equal to. Well, how do I multiply the top by cos? I have to distribute. Cos times 1 is cos. Cos times cos gives me cos squared. How do I multiply the bottom by cos? I have to distribute. Cos times 1 is cos again. Cos times 1 over cos is just plus 1. So in this technique, you get rid of the extra fraction, and now we've got a single fraction. But in this technique, once you have your single fraction, it's still not equal to the other side. And you have to factor out the common factor of a cos on top, and then the cos theta plus 1's cancel, and so our left side is equal to our right side. Nice.